So here in section 5.4, we finally bring this all together officially, the connection between integral calculus and differential calculus. To understand really this connection, first we have to think about a function that might be defined with an integral. So remember that a definite integral just means to find the area under a curve between two input values. So I could find the area under f of x between a and b. So imagine, in this case here I have looks like a velocity function. Velocity is the function given by f of t, and I might want to find the distance traveled by whatever particle this is between time a and time x. So to find distance traveled, I would find area under the velocity curve. If I wanted to know, for example, how far the particle traveled between time a and time 2, I would find this area, the area under the velocity curve between a and 2. Well, later, if I wanted to find out how far the particle traveled between time a and time 4, I would find this area, the area under the curve between a and 4. Later, I might want to know how far the particle traveled between time a and time 6 or 8 or 10. And it might be that I want to find that distance traveled for a whole series of input values. So I might write a new function where capital F of x is the integral from a to x, so the area under between a and x, some curve, so in this case f of t. And notice the variable here isn't the curve that I'm finding the area under. The variable tells me how wide an interval I should find the area over. So imagine that we could define, we saw one of these in the last section, a function that is an integral whose upper limit is the input variable. Okay, so here it is, the connection between integral calculus and differential calculus. Essentially what it is, integrals and derivatives undo each other. Integrals and derivatives are inverse operations, just the same as sine and inverse sine, or squaring and square rooting, or natural logs and exponentiation are inverse functions. So what that means for us, and what the fundamental theorem of calculus summarizes for us, is that integrals undo derivatives, and derivatives can undo integrals. So we essentially say those two things, integrals undo derivatives, and derivatives undo integrals, with the two parts of the fundamental theorem of calculus. So notice here, this happens to say that this is part 1. Nobody actually agrees which is part 1 or part 2, but there are two parts and you have to know them both. So this part of the fundamental theorem of calculus, and it goes on your green paper, says essentially that if you have a function defined with an integral, so a function like this one that we just talked about a second ago, where this says find the area under the f of t curve, but the thing that changes is how far you're going to let x go, how far that upper limit is from the lower limit. If you were to take the derivative of that integral, the derivative and the integral would undo each other and leave behind what's inside the integrand. So basically the f function, but notice that my output variable, it was a t in here, but now it's changed to whatever that upper limit variable is. So check out how fast this can be. There are a couple of rules that a couple of criteria that have to be in place before you can use this. But when it works, it's super fast. So if I want to take the derivative of an integral and the upper limit of the integral matches the variable with which I'm trying to differentiate with respect to. So here I'm finding d dx, the derivative with respect to x, and my upper limit happens to be an x. So that's one criteria. The variable for the differentiation has to match the upper limit of the integral. And the lower limit of the integration, the lower limit of the integral has to be a constant. So if you're taking the derivative of an integral and the variable of the differentiation matches the upper limit of the integral, and the lower limit of the integral is a constant, then we can use the fundamental theorem of calculus to simplify that expression super fast. What happens is the inside of that integral, which we call the integrand, the function, the f function in this case, is the output. The derivative and the integral undo each other, and what's left behind is whatever function was inside the integral. It's just that its variable changes to that, whatever that upper limit was, whatever that variable was. So the derivative with respect to x of the integral from a to x of f of t dt is f of x. The derivative and the integral undo each other. So we're going to do a bunch of examples here. So this one, I'm going to show you the long way, and then we're going to see how fast it can be with the fundamental theorem of calculus. So what if I wanted to take the derivative with respect to x of the integral from negative pi to x of cosine t dt? Well, I can actually evaluate that integral. We learned how at the end of the last section. And then at the end, take the derivative. So that's what I'm going to do here. This is the long way. The antiderivative of cosine t is sine of t. So notice here this d dx is waiting very patiently at the end. So I'm going to evaluate the integral, and then at the very end I'm going to take the derivative. So I'm going to evaluate sine of t from negative pi to x. So that means I'm going to find sine of x and subtract the sine of negative pi. So sine of x minus, the sine of negative pi is 0. So I have sine of x minus 0. My new problem is find the derivative of sine of x. Well, the derivative of sine of x is cosine x. So this is my answer the long way around. Watch how fast it is if I recognize that taking a derivative and integrating undo each other and just leave behind the function that was inside. So check. Number one, I'm taking the derivative of an integral. That's what this symbol means, right? d dx means take the derivative of. The variable for the derivative, the x down there, that matches the upper limit here. And the lower limit is a constant. The lower limit there is pi. So all three of those conditions are met. I can apply the fundamental theorem of calculus. And the fundamental theorem of calculus says that, there we go, I got in the wrong spot. The derivative and the integral undo each other and just leave behind whatever the integrand was. The integrand is the function inside the integral, but with a variable change. So instead of cosine t, cosine x, which you can see is the answer we got is when we did this problem the long way around. All right, so try the next example here. There we go. I guess the answer is already printed there. So here, if I want to take the derivative of this integral, I'm going to check that all three criteria are met. I'm taking the derivative of an integral. The variable, which is x, matches the upper limit, which is also x, and the lower limit is a constant. So all that happens is I'm going to replace the t's in that integrand with x's, and I get 1 over 1 plus x squared. All right. Now, there are a couple of possibilities. It could be that one of those rules isn't quite met, and we have a couple of ways to try to get around it. So here's one possibility. What if I want to take the derivative of this integral, but the upper limit is x squared, and I'm trying to take the derivative with respect to x? They're not a perfect match, but I can actually use the chain rule to evaluate this expression, to take this derivative of this integral. So if that's the only problem, notice I still have a lower limit that's a constant. I'm still taking the derivative of an integral, but the only thing that's wrong is that the variable that I'm trying to differentiate with respect to isn't a perfect match. The upper limit of the integral is a function of that variable instead of just the exact copy of that variable. Well, here's what happens. The derivative's still going to undo the integral. Cosine t is essentially going to be my answer, but the t is going to get replaced with that upper limit. So, and my answer here is going to be cosine of x squared multiplied by the derivative of that upper limit. In this case, the derivative of x squared is 2x. So the t's get replaced with the upper limit, in this case x squared, multiplied by the derivative of the upper limit. This answer is fine. If you're on the multiple choice section, they're going to rearrange it like this.